So what you're going to be doing is very, very similar to solving just regular equations. If they didn't have a radical in them, you're going to follow the same steps. So you can kind of pretend like the one that's on my screen. And if you cannot see it, I'm writing it a little bit bigger. There it is. So the one that's on my screen, it's got a radical around just the x, and the -4 does not have a radical around it. So what, and this is very similar to what we did when we had absolute value bars as well. What you want to do is get the radical isolated. So if there's other stuff around it, you need to do the inverse operation. So I have a -4 or a -4 next to my radical. I need to move it first before I do anything else. You got to clean up around the radical. So to move the -4 to the other side, I would add 4 to each side. And now I would have radical x equals 7. Remember that to get rid of a radical, or the inverse operation, is to square it. So if it says square root, the inverse is to square it. So next I would square each side so that I will not have a radical anymore. The radical and the square cancel each other out. So I'm left with x, and 7 squared, or 7 times 7, is 49. Now, remember that a lot of times when we use squares and square roots, we have a second answer of negative as well. But if I were to put -49 under this radical, remember, you can't, at least at your level of math, you can't take a square root of a negative. So even though it says use a comma to separate answers, generally they don't put that if there aren't two answers. They should not have put that on this one. This one should just be 49, and that's it, because if it was -49, you would not be able to do this problem. So our answer, or my answer, is 49. It does have a solution, and all those steps is how I get it. So your number 2 looks something like this. I know you probably don't have the same problem as I do, but you have something where you've got a radical over everything equals a radical over everything. So this one's going to be a little bit different, because there's nothing outside of the radical that you need to clean up first. So if there's no cleanup involved, then your first step should be what we did as the second step on the other problem. And that is, I cannot get anywhere in this problem unless I square to get rid of those radicals. And I have them on both sides, so I need to square both sides. That means on each side, the radical and the square will cancel each other out. So I'm left with 4v minus 8 and 2v plus 12. Notice that the radicals just magically disappeared. They didn't really. You did a step of work to get them. It's been a while since we've had variables on both sides. You can do, I could subtract 4v, I could add 8, I could subtract 2v, I could subtract 12. Doesn't matter where you start. I like to start with my variables, and I like to start with my smaller variable. So the smaller variable for my problem is 2v. So I'm going to subtract 2v from each side so that I'll only have v's on one side, on the left. Then I would do the inverse operation to get rid of the -8. So I would add 8 to each side, which gives me now 2v equals 20. So v equals 10. And again, if I made that a -10, I would get negatives under my radical. So just plain old 10 should be my answer. And it is. So it already looks different because the x, or one of the x's anyway, is already all by itself, and there's no radical around it. So we're going to come up against a little bit more difficult of a problem because of that. I mean, it looks pretty innocent right now, but because I have to square both sides, I'm going to end up with an x squared, and we haven't had that so far. So just double checking, the x on the left is already by itself. On the right, there's a radical around the entire thing, so there's nothing to clean up to begin with. I need to square to get rid of that radical sign. And because you're squaring one side, you have to square the other, even though there's no radical there. To keep it a balanced equation, you have to square each side. So now we have this x squared. These two cancel each other out, and we're left with 2x plus 3. So guess what we're going to have to do, guys? We're going to have to factor. Before I do that, I'm going to move everything on the left and set it equal to 0, because I can't do anything with this problem if they're on opposite sides. So I'm going to keep the x squared. A positive 2x, if I move it over, will become negative 2x. And a positive 3, if I move it over, will become negative 3. And now we've got it in standard form. I know I said standard form for the warm-up. That's standard form of a line. What you're looking at now is standard form of a quadratic. So that, remember, this is a parabola, a U shape. Now I'm hoping I can factor. I could complete the square. I could use the quadratic formula, but because 3 is a prime number, factoring is the way to go for this for sure. I know it's been a while, so maybe you thought you're supposed to be adding, but remember, we're supposed to be decomposing or dividing. So that 3 has to break down into 3 and 1, or you could put 1 and 3. Some of you put 1 and then 3. At the front, x squared has to break down into x and another x. And then we have to figure out little and big smiley, or the O and the I in FOIL, to figure out how we're going to get that negative 2. So we're multiplying, multiplying, multiplying. So I've got a 3x for the little smiley, or the inside. I have a 1x for the big smiley, or the outside. And I need to get a negative 2x. The only way I can do that, and remember, we're putting pluses and minuses, so now we're adding or subtracting. The only way I'm going to get a negative 2x is to make that negative and that positive. Negative 3x plus 1x would give me the negative 2x that I'm looking for. So there are our symbols, x minus 3, x plus 1. You could use a box, you could FOIL, you could cover up to double check, but if you multiply that all back out, you do end up with x squared minus 2x minus 3. Those aren't our answers though. We need to figure out what would make these chunks equal to 0. So I'm going to switch colors so you can see real quickly. So this first chunk, what I could replace x with to make that circle, if you will, a 0 would be 3. 3 minus 3 is 1. And I'm sorry, 0. Sorry, I was looking at the next one. 3 minus 3 is 0. And then if I do that guy, to make the blue oval equal to 0, that x would need to be negative 1. Negative 1 plus 1 is 0. So there are my two answers. We now finally do have a problem that has two answers, 3 and negative 1. Even though they worked when we did the math, we have to see if they work when you're done. These things are called extraneous solutions. Let me write that. It's like extraneous solutions. And what that means is if you just do the math and you don't pay attention to what you're doing, you'll come up with two answers. But sometimes neither one of them really work if you plug them back in. So that's what happened on this one. If I take that negative 1 answer that we got, which worked when I did the math, and I plug it in here, I don't care what's under that radical. A radical cannot ever have a negative solution, at least not in algebra. So even though it worked when I did the math, negative 1 is what's called an extraneous solution, because it worked when I did the math, but it doesn't work when you plug it back in. So I'm going to close. I'm going to delete my negative 1. And now I have it correct. So this one's just like number 2, where there's nothing to fix around it because the radicals surround the entire thing. So you would just start by squaring each side. Those cancel each other out. So you're left, ooh, this was a good one to stick around for. Oh, well, too late. X plus 5 equals x minus 1. Here's what's gonna happen. If I subtract x from each side, they're gone. I don't have any more x's. And now I'm left with a statement that says 5 equals negative 1. Well, 5 does not equal -1. So that one would be no solution because there's nothing you can come up with that will work in that problem. And my guess is that your number 4 is probably also no solution because digits always does something, very similar for everybody.